is up, everyone? Welcome to week 58 of Chill Kernel Hacking for Fun. Today, we're going to look into DMA, and we'll be continuing with the network driver. I'm pretty excited about it. Before we begin, let me just make sure, as usual, that the streaming setup is set up correctly. Wow, Cat Flare, you beat me to making the first message in the chat. Hello, Cat Flare. Hope you're doing well today. I want to hear more about that EFI bootloader idea too. I find that super cool. Okay, test Twitch. Just sending my typical test messages in the chat. Jake, what is up, man? Hello. Thanks for joining. Wow, people are pretty punctual today. That's crazy. Yash, what is up? We got 6 people in the chat, and I've been online for like 1 minute. This is wild. We'll do a quick test of the audio board. Air horn. Applause.
Damn, son, where'd you find this?
Right. Kernel, someone cooking. Someone cooking.
This is a certified hood classic.
Let me know.
This is a certified hood classic.
I don't want that to be too loud, but if that's too loud, just let me know if that's annoying. All right. It looks like things are going well. We got our chat widget set up. We got Twitch streaming set up. We have YouTube going. And I got my messages on Discord. So I think we can get started. So, right, what is going on? So we are working through Lab 6 of the MIT course, which is the network driver. And last time we made a bunch of progress, and we actually scanned the PCI bus for the NIC and enabled it and mapped its registers into memory, and then did a single test read where we tried to talk to the NIC and read its status register. And we got that working. Let me see, how do I... What's up, Kidar Codes? Nice to see you. What do you think every developer needs learning data structure? Yeah, I mean linked lists. I'm just gonna say linked lists. Yeah. Careful. I'm using NYU EFI to make EFI image, but I have difficulties in converting PELF to PE. Interesting. NYU EFI. Never heard of that before. Okay. So here I'm running the kernel, and we can just quickly see, I guess make Kimu would just do it also. We can just see the result of reading the status register. It says 8008-783, which is exactly what it said we should get. Also, by the way, I'm really happy to inform you that I have fixed my build error from last time, and it no longer rebuilds the entire kernel every single time I run the kernel, which is a huge step forward. So now it successfully detects that there's nothing to rebuild, and it doesn't do anything. So, yeah. Kedar, how are you doing this work on a Mac? Okay, really simply, I'm using Kimu. Kimu works on Mac, and it's a system emulator, and I'm using an i386 GCC toolchain to cross-compile and build a x86 image, which I run in Kimu. Yeah, thank you. Thanks for the support. Converted ELF to PE, time to run this. All right, so let's get it moving. So today we're learning about DMA, apparently. That is what's up next. So that's kind of new to me, so we'll just take some time to learn about DMA. I'm also going to try to record the timestamps a little bit better of moments in the stream, so I can provide timestamps in the YouTube comments. And 6. Sorry. What's up, Afnan? Test 1. Good to see you. Okay. DMA. C or C++? I'm personally a C++ fan, actually. And this the soonest I can, I'll be switching over to C++ for the kernel, probably when I rewrite it from scratch. Because it's right now, like, it's all the course code. Okay. DMA. You could imagine transmitting and receiving packets by reading and writing from the registers, but this would be slow and require the E1000 to buffer packet data internally. Instead, the E1000 uses DMA, direct memory access, to read and write packet data directly from memory without involving the CPU. So I always find it helpful to illustrate stuff like this. I'll do my best. So just quick illustration, we have the CPU, we have the device, network, the NIC device, and we have main DRAM memory. We have a DRAM device, which is aka main memory. And these are all different things. And typically, and obviously the CPU is connected to DRAM, but also the NIC is connected to DRAM and can actually read and write memory. I guess there is technically like a memory bus, something like this. Very broad strokes. CPU is connected to the memory bus. The memory bus has a bunch of stuff connected to it. DRAM being one of those things. The NIC is also connected to the memory bus. And so the CPU and the NIC actually have a communication channel. It's via the memory bus, but this is the I guess my text is like kind of small here. Text. I'll just add a text. This is MMIO registers. So the CPU can talk to the NIC via MMIO registers. The NIC, however, can talk to the DRAM main memory via DMA. Also, so this is kind of a map of the connections we have here. And then maybe actually this thing is more confusing than helpful. And then obviously the CPU can access DRAM also. Memory access. So this is approximately what things look like. And what we're specifically talking about here today is the DMA connection, where the NIC can access memory. Right. Right, okay. Let's keep reading. So the driver is responsible for allocating memory for the transmit and receive queues, setting up DMA descriptors, and configuring the E1000. I'll also make sure our break timer is going. Okay, transmit, receive queues, setting up DMA descriptors, 3, configuring the card with the location of these queues. After that, everything is asynchronous. To transmit a packet, the driver copies it into the next DMA descriptor in the transmit queue and informs the E1000 that another packet is available. The E1000 will copy the data out of the descriptor when there is time to send the packet. Likewise, when the E1000 receives a packet, it copies it into the next DMA descriptor in the receive queue which the driver can read from at the next opportunity. I also have I have the manual here, but I don't know if that's how truly helpful this is going to be. It would be neat if there were some diagrams. This is physical. Here, right, and oh, I think I even took a screenshot of this last time. Or maybe I didn't. So anyway, this is the fundamental general concept of what's going on here. We have these circular buffers, and actually we have two. We have one for transmitting and one for receiving. And that's how we interface with the NIC. Okay. Transmit and receive queues are very similar at a high level. Both consist of a sequence of descriptors. While the exact structure varies, each descriptor contains some flags and the physical address of a buffer containing packet data. Okay. So it's basically a pointer to a buffer. Either packet data for the card to send or a buffer allocated by the S for the card to write a received packet to. Welcome, hello to the 2 viewers on Twitch and 13 or so on YouTube. Thanks for joining. Shout out to the Twitch people. Also, I'm super new here on Twitch, so I don't have many viewers here. Okay. All right, so we have basically these buffers, or it's really a queue data structure where like a FIFO, like things come in and then things come out, and they are processed in the order they are pushed into the FIFO. And we're pushing these structures which point to a buffer of memory. So yes. Queues are implemented as circular arrays, meaning that when the card or the driver reaches the end of the array, it wraps back around. Both have a head pointer and a tail pointer, and the contents of the queue are the descriptors. The hardware always consumes descriptors from the head and moves the head pointer, while the driver always adds descriptors to the tail. Okay, so that's super important. I'm just actually going to copy that. I'm going to screenshot this for special reference. Hardware consumes from the head and moves the head pointer, while the driver always adds descriptors to the tail and moves the tail pointer. Right, so here's like some base address, memory is going up. When we push data in, we are pushing them at the end and incrementing the tail, right? So in this receive queue, okay. Okay. The descriptors in the transmit queue represent packets waiting to be sent. Okay, in general, transmit queue is empty. And then we're pushing things into the queue to be sent out in the, okay. And so we're pushing into the tail, the hardware pops up the head, and so the hardware is always consuming from the head. So in the transmit queue, we're pushing things onto the end of this queue. Hardware is popping things off the front of the queue from the head, and we're pushing packets out to send from the receive queue. That's interesting. The descriptors in the queue are free descriptors. So they point to buffers available for data to be written to them. And we push a bunch of these free buffers in there or something like this. And then when hardware has data, it pops an entry off basically and then writes to that buffer. And then somehow we need to process it or get notified to process it. The card can read. Okay. So in the steady state, the receive queue is completely full of all available receive descriptors. Correctly updating the tail register without confusing it is tricky. Be careful, okay. Pointers to these arrays as well as the addresses of the packet buffers must be physical addresses because the hardware performs DMA directly to and from physical RAM without going through the MMU. Interesting. Transmitting packets. Okay. Transmitting packets. The transmit and receive functions are basically independent, so we can work on one at a time. We'll attack transmitting first because we can't test receive without transmitting an I'm here packet first. First, you'll have to initialize the card to transmit, following the steps described in section 14.5. You don't have to worry about the subsections. The first step of transmit initialization is setting up the transmit queue. The precise structure is described here, and the structure of the descriptors is described there. We won't be using the TCP offload features, so you can focus on the legacy format. You should read those sections now and familiarize yourself with those structures. Okay, let's take a look at those structures. So initialization, init, queue, descriptors. So 14.5, let's see what that looks like. 14.5, transmit initialization. Okay, allocate a region of memory for the transmit descriptor list. Software should ensure this memory is aligned on a 16-byte boundary. Program the transmit descriptor base address registers with the address of the region. Okay, this is already, so I'll screenshot this for reference. So maybe, yeah, base address registers, TBAL, for 32-bit addresses, and both AL and AH are used for 64-bit addresses. Set the length register to the size in bytes of the descriptor ring. This register must be 128-byte aligned. The transmit descriptor head and tail registers are initialized by hardware to 0. Software should write 0 to both to ensure this. Interesting. Okay. Initialize the transmit control register for desired operation to include the following. Okay, so we just have a bunch of initialization we need to do. Okay. Okay. Anything else there, or there's some other stuff here, but what did it say? Okay, don't worry about the subsection. So okay, that was the first one. So we have basic card initialization. Just quickly checking Twitter in case anything happened there. All right. So number 2, the queue structure. So far, all we know about the queue is that it's 128 byte aligned. So the length must be at least 128 bytes. Okay, 3.4. The transmit descriptor ring structure is shown in this figure. A pair of hardware registers maintain the queue. New descriptors are added to the ring by writing descriptors into the region and moving the pointer. The tail pointer points one entry beyond the last owned descriptor, but at a point still within the ring. Transmission continues up to the descriptor where head equals tails, at which point the queue is empty. Descriptors passed to hardware should not be manipulated by software until the head pointer has advanced past them. I will just copy this also. This is our handy diagram, as usual. What is up, aggressive cat? Welcome. Shaded boxes. I'm reading, this is the manual for the E1000 network interface card, which we are writing the driver for. Transmit descriptor ring. So the shaded boxes represent descriptors that have been transmitted but not yet reclaimed by software. So we push a bunch of buffers, which means that hardware now owns them and is eligible to read the data and modify the descriptor. So we can't touch anything here. As software, what we can touch is these shaded boxes, because those are the ones that, so they're like free slots which we can transmit packets from, and get reclaimed by software. Interesting. Because so that the tail starts, so the tail marks the end of the queue, and as the OS driver, we are interested in the free, we're always interested in the free slots, basically, that are owned by us, which is from the tail, starting from the tail and ending at the head. The descriptor ring is described by the following registers. Address, okay, this is worth copying. Okay. So address, base address, 16 byte boundary, 64-bit address, okay. Hardware, so we're probably only interested in 32 bits. The length, head, and the tail, right? Which is an offset from the base and indicates the in progress descriptor. there can be up to 64K descriptors in the buffer. That is interesting. Reading this register returns the value of head corresponding to descriptors already loaded in the output FIFO. Okay. Tail, location beyond the last. Yeah. Base register indicates the start of the circular descriptor queue. Yeah. Lower 7 bits are hardwired to 0 because of this alignment requirement. Byte addresses within the descriptor buffer are computed as follows. Base plus pointer times 16. So I guess each of these descriptors is 16 bytes. It's my understanding there. Size chosen for the head and tail, permit maximum of 64K. Given an average of 4 descriptors per packet. Okay. Points 1 pass. Okay. Software can determine if a packet has been sent by setting the RS bit, checking the transmit descriptor DD bit eliminates a potential race condition. So there's different bits. Interesting. All descriptor data is written to the I/O bus prior to incrementing the head register, but a read of the head register could pass the data write in systems from I/O write buffering. Updates, the descriptors use the same I/O write path and follow all data writes. Okay, apparently there's some deep discussion of race conditions here. Okay, In general, hardware prefetches packet data prior to transmission. Hardware typically updates the value of the head pointer after storing data in the transmit FIFO. So storing data, okay. Transmit. So the transmit FIFO is different. That's actually a FIFO on the device, I believe. Okay, I don't... Yeah, this is not talking about the transmit queue, I believe. Okay. For checking completed packets consists of one of the following: scan memory for descriptor status writebacks, take an interrupt. Okay. So those are some details, deep details. And that brings us to our first 20-second break to stand up and remember to stretch. So I'll be right back. Okay, so deep details on the queue, and lastly, structure of the descriptors themselves, 3.3. Legacy transmit descriptor format. To select legacy mode, we should set this certain bit, so that's important. In this case, the descriptor format is defined by table 3.8. Address and length must be supplied by software. Bits in the command byte are optional, as are the checksum offset and checksum start. Right, so it is a 16-byte structure. And half of it is a buffer address, which is 64 bits. So we're not really caring about, we're using 32-bit. So all our addresses will have zeros for half of it, probably. I am curious about the endianness here, but I will just assume it's little endian, I think. Yeah. And then we have some fields, and it said that some of these are optional, but address and length are required. Address and length, okay. And interesting, so you can have a 16-bit length, and that's the maximum size. Or yeah, so like 64K or something like that. 16 bits of length per segment. Okay. Total length. What's up, Anatoly? Okay, so we got the length, we got the address and the length, and the length can be up to, it's not actually the full 16 bits. Or wait, what? So I am kind of confused. 16 bits is 64K, right? Oh, 16, yeah, that bytes, right. Just out of curiosity, times 8. So that's a length in, I think I'm still kind of confused what is going on. The maximum length associated with any single is 16. So even though we have 16 full bits here, we are significantly underneath the maximum that can be represented by that field. So that's confusing. Okay. Okay. So I think that's all we need to really care about there. Then we can do command, right? Command, so there's space for commands, although it's optional. And what are some examples of commands? Wait, is it a single byte? I think there's a single command byte, which means there are 8 commands. Interrupt delay, VLAN packet enable. Okay. Report packet sent. Report status. Checking the descriptor done bit. Status byte. Insert checksum. Okay, there's some other options that are possible. And then there's a status. Status byte, I suppose. right? 32, 36. So wait, no, it's that is half a word, right? 4 bits for the status. Okay, and then there's some status including all sorts of stuff. Okay, so that's a basic overview. Okay. Okay, so now we understand some of these structures. It will be convenient to use C structs to describe these structures, and we can do that. With packed. Right. Okay. Here they give us an example of the transmit descriptor, where it has a 64-bit address, then all these different things. And yeah, just to be really clear. Yeah, so this is the beginning of the descriptor. And so it goes, like memory goes, like higher memory addresses are lower in this diagram. And so the first thing is going to be a 64-bit value, followed by all the rest of these things. Right. Starting from 0 here. So you read it like actually right to left, kind of. Yeah. I probably would have made that mistake with the ordering. Okay. Driver will have to reserve memory for the transmit descriptor array and the packet buffers pointed to the descriptors. Several ways to do this, ranging from dynamically allocating pages to simply declaring them in global variables. Whatever you choose, keep in mind that the E1000 accesses physical memory directly, which means any buffer it accesses must be contiguous in physical memory. And so that what this is like hinting at is that if you have a buffer that spans multiple pages, all of those pages need to be contiguous in physical memory. You can't have a region of virtual memory that's backed by like a bunch of different physical pages. Interesting. I always kind of wondered that, actually. I knew there were some, for example, if you're doing Linux kernel development, there are some allocator APIs that allow you to guarantee that the memory is contiguous in physical memory. But I never really understood why you would really need to care about such a thing. But this is a good example of interfacing with devices that do DMA. Okay. Simplest is to reserve space for a packet buffer for each descriptor during driver initialization and simply copy packet data into and out of these pre-allocated buffers. The maximum size of an Ethernet packet is 1518 bytes, which bounds how big the buffers need to be. More sophisticated drivers could dynamically allocate packet buffers, or even pass buffers directly provided by user space. But it's good to start simple. Okay, and we've reached exercise 5. Perform the initialization steps described in section 14.5. Use section 13 as a reference for the registers. The initialization process refers to in sections 3.3.3 and 3.4 reference. Okay. Be mindful of the alignment requirements on the transmit descriptor array and the restrictions on length of this array. Okay. Need to do some multiple of 8 transmit descriptors. So, right, because it's 128 bytes aligned. The descriptors are 16 bytes each, and then 8 of those is 128. Don't use more than 64 descriptors, or our tests won't be able to test the transmit ring overflow. Okay. Cool. So there's a lot to do here, but let's just begin slowly with making sure we have some of these structures available. So PCI, this is all PCI stuff, which is not Wolfenhaus. We are writing the driver for the NIC. And so I'm just going to assume we don't have this type already there, right? So we need to define it. So I guess, yeah, that's what we'll do. I'll just copy this one. Good life. Thank you very much. I'm trying my best. Okay. Type def struct. It's called, and I'm gonna give it a different name, I think. From Silent Viewer from India. Thank you for watching and the comment and not being a silent viewer. Right. Okay. So transmit descriptor. That would be a super verbose name. TX descriptor. I kind of like the prefix. Maybe I'll just keep it this simple. Okay. So that is. I'll just take a moment to clean up some of these variable names. So, adder. Right. Buffer adder. Oh, did not want to do this crazy thing. Okay. Buffer length. This is 3.8. What? Legacy transmit, right? Like checksum CSO. Status CSS special checksum offset. Right. Checksum offset. Command field status. Command status and CSS is checksum start. Check some start. So we have our, this thing. Attribute packed. It's not technically necessary, but yeah, but we want it to be packed. We need it to be packed. Okay. So that is a nice gentle introduction to this. So we have some more structures to describe. So let's just take a baby step and do that. So let's go back. Let's just go back 415. Were there any structures there? It's really not. I guess it's really not that many structures. It's like the descriptor is the main structure. Yeah. And actually, I'm going to even rename this to buffer phys adder for the moment. Technically, I might use my phys adder type, but that's 32 bits, I think, phys adder t. Wait, what? T. It's like, yeah, it's a uint. It is defined somewhere here. I think right here. Okay. The structure of the queue. But the thing is, we don't really have an actual C struct for that. Okay, so now, allocate a region of memory for the transmit descriptor list. Software should ensure this memory is aligned on a paragraph boundary. Right. So first of all, how should we do this? It gave us a recommendation. Reserve space for a packet buffer for each descriptor during driver initialization. Simply copy packet data and out of these pre-allocated buffers, right? So pre-allocated region, rather than having it be dynamically sized. So the question is, how many packet buffers do we want? Don't use more than 64 descriptors. Don't use more than 64. All right, palm tree break. Be right back in 20 seconds. Okay, I'm also just going to set a timer for myself. Yeah. I need to leave a little bit earlier today. Okay. So let's just think. So we need a couple things. So we need a buffer of memory for the packet data buffer for the transmit queue, right? And then each of the descriptors points at a buffer. And so what I'm thinking is we're just going to allocate a large region of memory, and then these descriptors are going to point just to offsets within that memory. Okay, so we have some constraints. So 16 byte. So this is on a 16 byte boundary. Transmit queue. Wait, yeah, no, this, right, sorry. This is the thing that's on a 16 byte boundary. This is probably just going to be page aligned, or I'm not quite sure what the alignment of that will be. Okay. So really, the main questions for me right now are how big are these buffers? How many of them are there? And like and also how many descriptors are there? Maximum size of an Ethernet packet is 518 bytes, which bounds how big, right? So that's a good hint. 18 bytes max. So what's the easiest way we could start? Let's just say we wanted to have enough space to transmit a single Ethernet packet. So that means it needs to be at least this large. And I'm just thinking I probably want some like very even number. Like what if it was 2K bytes, for example, like half a page, or maybe let's just say it was 4K. That sounds like a reasonable buffer size to me. Just make it a page. So I'm just gonna say, we're just gonna make that 4K. So that means, so that's the total space. And then now we need to decide how many descriptors we're going to have. We know that there's a maximum of something kind of huge, like 64K, which sounds really large. I feel like for simplicity, for starting out, we should be choosing a much smaller number, but also probably a power of 2. Let's just, I'm kind of like totally guessing here, but let's just say, for example, for purely starting out, that we have 32 descriptors. Right, so that means that we're going to have 4096 divided by 32 is 128 bytes per descriptor. Okay. So that's at least sort of a start. Oops. Okay. Settings opened up. Okay. So, yeah. So that's something we can work with. Also, what's up, Ragu? What's up? Thank you for joining. Okay. So now it's time to actually allocate that memory. And where would I do that? So I have a bunch of options. But also in general, I'm sort of a little bit confused about the structure of the code here. Because I guess we are just running all of this code within this callback that's called to us during PCI bus scanning. And we're going to block PCI bus scanning, but we need to initialize our driver. So I'm just going to, I sort of feel like doing this in a little bit of an object-oriented way. Right, so I already have my header. Wait, something weird happened. Oh wait, no. I used to have a bit of code. I think I stashed it actually. Let me quickly, was it over here? Yeah, here I was playing around with some improvements here. I kind of want some of this stuff, so I will make a custom patch, but I didn't want the whole thing. I'm going to zoom out a little bit. So I want these in my custom patch. This is like all playing around, some comments. I want these in my custom patch, and I don't care about this. So now I can go back here, patch options. Oh shit, wait, did I do that right? Yeah, so now I want to just apply that. Copy flash to the clipboard. Apply patch. Yeah, I think that's what I wanted. So now I have that patch applied, and I had this change I make, which now introduces this structure to contain the driver state instead of using a bunch of global variables. I just wanted to quickly check that this still compiles. And now we have packed attribute ignored. Is this the syntax? I think this might be the syntax. Okay, yeah, that's the syntax. Note the lack of rebuilding. So we've repacked. Actually, yeah. I'm gonna call this P buffer, actually. Fizz. Something weird like that. Okay. So now what I want to actually do is make an init function. So I was just kind of playing around with some stuff here. But now I'm going to actually make a function. Also, we have this random constant, which is not amazing to just have here, but I'll just keep it up here. All right, void e1000 init, and we'll take an e1000 driver. And then we're just gonna call this, yeah, e1000 init with the g e1000. why is it? Argument of type. Oh wait, I need, of course I need, right. So I'm just trying to avoid the global variables proliferating throughout the code. So I'm trying to just explicitly pass things when I can. And so we have, so this is our example of using mapped.io. It would probably be good to write some helper functions to help us with this kind of stuff, because we're kind of doing it very raw right now. But we can fix that as we go. So the first question was memory allocation. The idea was to allocate a page of memory for the backing buffer for the driver. And there's a couple different options we have. We could statically allocate the memory in a global variable, which I'm sort of loath to do, because it blows. Well, actually, if it's in the BSS, it should not blow up the binary size. Maybe that would, maybe we can try that actually. So in here, we're just going to allocate a massive buffer. Right. And what's a better name for that? It is the transmit transmit buffers. Well, really, it's an array of several buffers. So I'm having because I'm like hard coding a lot of this right now. So whatever. I'm just going to call it the transmit buffer for right now. Okay, so we have our global memory, and we need to do what? So we need to make a checklist for myself to allocate the backing buffer, allocate the descriptor ring, initialize all descriptors, initialize all MMIO registers, necessary. So we've initialized so we've allocated the backing buffer. But we need to still initialize the transmit descriptor list. So I'm just going to slowly try something, which would be I guess, which would just be another global variable, which it would be the easiest way to do this. And it would be an array of E1000 transmit descriptors. And we want 32 of them because that was the arbitrary number we wanted, to ensure these are aligned. right? So there's probably some way we can do that. So MMIO constant. Yeah, just kind of being all over the place here. But then we have K, num tx descriptor is 32, right? K tx backing buffer size 49.6, maybe page size. And I'll call this GTX and G for the moment, since they are global. Right. And then we had some alignment requirements. The size in bytes of the descriptor ring. So are we? So we need to have. Wait, we need to have at least, right? It was like 8 or something. Multiple of 8 descriptors, and we have 32. So that's valid. Memory is aligned on a paragraph. So that's the one thing we need to make sure. How do we ensure this is aligned on a 16-byte boundary? I'm just going to ask, maybe I'll ask cursor. How do you, was it command I? Add to chat or edit. I want to edit. Make this aligned on 16-byte boundary. Right, align as, accept. Frame buffer, what is up? Thanks for making it. Okay, so we have alignment requirements for the actual backing buffer, which is described here. Wait, I am getting so confused. The transmit descriptor list needs this. Okay. So let's just, and then we need to program these registers with the address of that region. Let's just try to do that. So flipping back and forth. One thing I'm not sure of is if we have any constants anywhere, but I think it seems like we actually just don't. So yeah. So we need to look up where these registers are. And it tells us section 13. Register conventions, main register descriptions. Transmit. Here we go. Actually, wait a second. No, we already, So they gave us the advice to use Kimu as a reference for a lot of this stuff. So maybe that would be good to do. So I'm just going to copy this file and make duplicate file. We'll call it the exact same thing. Okay, so apparently this was also copied from somewhere else. From Intel. So this has an incredible amount of stuff we do not actually need. But it's time for a 20-minute stand-up stretch and some water. Be right back. Right, so we have a lot of constants we do not need. But maybe then that speeds this up a little bit. So we need a couple register definitions. We need transmit descriptor base address TDBAL. Let's find that. Transmit descriptor bit definitions, transmit control base. Okay, I don't even see. Okay, maybe that isn't even faster. We need 3804 hex. Why is that not even there? That is very confusing. So is there something I'm doing wrong here? Or is it possible? Or is that the wrong file? Oh shit, that might be the wrong file. Okay. This is looking right. Okay, that's the right file. So we have this. We need to edit our make file. Source files will have 6, but actually I guess we don't need to declare header files here. But also, why is it E100? That doesn't even exist. Okay, whatever. So we're going to include our registers, or register information. And I can't find it. Oh, but that's because there is this dependency. Oh, that kind of sucks. All right, I'll just create it too, and we'll try to move forward. Do this thing, and then now this thing finally is there. Ismail, what is up? Good to see you, my guy. So we can now convert at least this thing, I think. This is the status register. Status? Something about this. Bit definitions. I don't even think using these header files is speeding things up. It's like so hard to find anything in there. So maybe that was all a bit of a distraction, but yeah. I'm muted. Oh, I'm muted? Okay. Have you scared there for a second? Okay. So this ought to be very easy, but before we... So basically we just want to do something very simple, right? We want to set these two registers to the addresses of the descriptor list. So for example, it's going to look something like this, where we want to get some constant and TBDAH. There's like a million of them. Okay. TBDAA, TDBAH. 38, which is the 3804 thing we wanted. High and low. So in this case, it's really just the low register. And there's this weird alias thing. So anyway, this is our symbol. Is equal to the address of GTX descriptors. And then H is just going to be equal to 0. But of course, we probably want a bit of a better way to do this. Like, this is so unfortunate. That we need to access it in this way. So what we really want is like a function that reads and writes at an offset. So I want something like write word or something like that. And we would just pass it the GE1000 PMMIO base 1000. We pass it this thing. Yeah, we would just do something like this. And then we have like an offset, but right, it's we need to specify the width usually. Okay. My timer's going up. I need to leave in a couple minutes. I'll set the restart. what? I'll set like a 9-minute timer. Okay. So I might want to write various widths. I guess it's like write 32, for example. And then I guess it's the uint32t data. And here it would just be technically it's p base. So p base plus offset with data. Made this a char. But then I need to convert this to uint32t pointer, for example. So I think that would allow something like this to actually work. Again, just really sketching it out in a pretty raw kind of way. But my goal was just to, I guess it's declared kind of weirdly as a uint32t pointer. That probably should maybe be different. It's really just a random pointer. It's a base address pointer. Yeah. Whatever, I'll leave it like that for the moment. So that's us off to our gentle start with writing these registers, the address of the region, what's next? Set the length register to the size of the descriptor ring. So that's not too hard. That is td_len. Okay. And this is the size in bytes of the descriptor ring, which is size of this. Yep. Okay. The head and tail are initialized by hardware to 0 after power on. We should write both of them. Okay, we can do that. So, oh shit, what is it? Oops, I just quit VS Code. Oh shit. Just quit VS Code by accident. Okay. TDH. There's all these aliases and other stuff. Okay, TDH is 0 and TDT? Is that something? Tail descriptor tail. Initialize the control register to include the following. Set some bit to 1. Set some bit to 1. What is it? 3. 14.5. Configure. Oh, Sia Kadar. Okay. Configure this to something. Ethernet standard is 10H. Configure this other thing. I don't know what that's talking about, but okay. So let's take the control register and preview. Yeah, it would probably be nice to have a second copy of this document. TCTL. So it's another 32-bit register. So we can also have like a write 32 or read 32. Went 32T. Turn this. And here's where we get the, just gonna call it val, read 32, a base, E1000, TCTL. And then we're just going to, or maybe, then it's gonna be very similar. Write 32, add TCTL with TCTL or I was just pausing because there's probably a easier way to do this with like a or equals or something like that. But whatever. Okay, so we need to set enable bit. GC. Enable TX to 1. Okay. PSP. CT. Huh. Okay, so wait a sec. So and CT is these things. Okay, so maybe I need a structure for this actually. Have I written drivers before this? No, not really. I am like loosely familiar with the idea, and I've written a bit of Arduino firmware before, which is somewhat similar in terms of writing and reading these registers, but no, never written a driver before. So actually, it sort of seems like it would be useful to have a structure. Control bits. But I feel like I'm missing something. For example, I'm not seeing PSP. Or is that in this block here? It's the block of control bits. Okay, and it's 5:30. That means I gotta go, y'all. So I'm gonna end the stream here a little bit early today, but I wanna thank you for joining the stream. And thanks for watching me slowly write this driver and learn how to write drivers. I'll be back again next week and we'll continue with working on this driver. So I'll plug myself briefly before I leave. I have a Discord server. Feel free to join it to stay in touch. Thanks, Brain Buffer. Yeah, have a great week, y'all, and I'll see you next time. Peace.